diving into one of the most influential papers in modern AI. It came out in 2014 and introduced an algorithm called ATOM. And I'm not exaggerating when I say that this one idea is one of the key engines running behind the scenes of the entire deep learning revolution.
Okay, so let's just jump right in. It all boils down to this huge but kind of simple challenge. When we train a neural network, for anything from recognizing cats in pictures to powering a huge language model, what we're really doing is just searching. We're searching for the perfect set of internal knobs, or weights, that make the model do its job in the best way possible. And we're talking billions, sometimes trillions of these parameters, which creates a search space that is just unimaginably complex.
The best way to picture this is to imagine a blindfolded hiker. They're standing in a massive, invisible mountain range, and their only goal is to find the absolute lowest point, the deepest valley. So that's really the core problem we're trying to solve here: optimization. This mountain range is what we call the lost landscape. Every spot in the range is a different setting for the model's knobs, and the altitude is basically how wrong the model is. But here's the catch. Our hiker's blindfolded. They have no map. All they can do is feel the slope of the ground right under their feet.
Okay, so our hiker's in a tough spot. To get out of it, they're going to need a strategy, right? A set of rules for how to take each step to make sure that they are consistently, step by step, moving downhill towards that lowest point.
All right, the most basic tool in the hiker's toolkit is something called gradient descent. Now, gradient is really just a fancy word for the slope of the landscape right where the hiker is standing. So the strategy is dead simple. Figure out which direction is the steepest way down and take a small step. Then you do it again and again and again. And in theory, you should eventually end up at the bottom.
But as you can probably guess, this super simple approach has some pretty big problems. If our hiker is on a big, flat plateau, the slope is almost zero, so they end up taking these tiny, painfully slow steps. Then, if they get into a steep, narrow ravine, the slope changes like crazy, and they start overshooting, just bouncing back and forth like a pinball. And even worse, they can get stuck in a flat spot, or a small dip that isn't the real bottom, and just think their job is done. So clearly, our hiker needed some upgrades, right? They needed to get smarter, and researchers came up with 2 key improvements to help them move more intelligently, giving them a better sense of both memory and the terrain around them.
And this led to 2 really key ideas that came before ATOM. On the one hand, you have momentum, which is all about remembering which way you were going. And on the other hand, you have adaptive learning rates, which is about changing your step size depending on how steep it is. Let's dig into momentum for a sec. Instead of only looking at the slope right now, momentum keeps a running average of the slopes from the past few steps. The best way to think about it is like turning our hiker into a heavy bowling ball. As that ball starts rolling downhill, it builds up speed, it builds up inertia. And that inertia is what helps it blast right across those flat areas and roll over little bumps that would have trapped our normal step-by-step hiker. Now, the other big idea, which you see in algorithms like AutoGrad and RMSProp, is like giving our hiker a pair of magic smart shoes. These methods adjust the size of each step for every single direction independently. So when the terrain gets really steep and treacherous, the shoes automatically shorten the stride to take small, careful steps. But when the hiker gets to a wide open, gentle plain, the shoes let them take these huge leaps to cover more ground faster. So for a while, it was like you had to pick one. Do you want the heavy ball or the smart shoes? They were 2 different approaches. Then, in 2014, this paper comes out with a new algorithm that just brilliantly fused the 2 together into one incredibly effective package. And they called it ATOM. It stands for Adaptive Moment Estimation. And as that name kind of hints, its secret lies in how it estimates and uses these statistical moments from the slopes to guide the hiker's journey. And this was a total game changer. Seriously, it gave our metaphorical hiker the absolute best of both worlds. Now they had the inertia of the heavy ball to power through tricky spots, and they had the smart shoes to perfectly adapt their stride to the terrain in every single direction. So how in the world does ATOM actually do this? What's the secret sauce here? Well, the answer is right there in the name. It all comes down to those moments. So let's pop the hood and see what really makes this thing tick. Okay, so the name Adaptive Moment Estimation gives us a clue. These moments are just a term from statistics. ATOM keeps track of 2 of them. The first moment is basically the average gradient. You can think of this as the momentum part. It tells us the average direction the hiker has been moving. The second moment is the average of these squared gradients.
This is the adaptive part. It tells us about the shakiness or the choppiness of the terrain.
So here's how the Adam algorithm works step by step. First, it figures out the slope for a small bit of data. Then it uses that slope to update its running average for both the direction, the first moment, and the shakiness, the second moment. Then it does this really clever correction step we'll talk about in a second, and finally, it uses those two corrected numbers to figure out the absolute perfect step to take next.
And this formula right here, this is the magic. The final step our hiker takes is based on that average direction, the momentum. But, and this is the key, it gets divided by a number based on that second estimate, the shakiness of the terrain. So what that means is if the terrain has been really shaky in one direction, the step size in that direction gets smaller. If it's been smooth, the step size gets bigger. It creates a custom-tailored learning rate for every single parameter in the whole model. But there's one more little detail that is just so clever and so important: biased correction. See, because those running averages for direction and shakiness both start at 0, for the first few steps they're a little bit wrong. They're biased. And without a fix, that could make the hiker take huge, crazy steps right at the beginning. Adam's correction step neatly fixes this, making it stable and reliable from the moment you hit go. So you get it. It's a really elegant combination of ideas. But the question is, why did it just completely take over? Why did Adam become the dominant default choice for pretty much everyone doing deep learning? Well, a big part of the answer is just look at the numbers. As of right now, the original Adam paper has been cited over 135,000 times. That makes it one of the most cited papers ever. Not just in AI, but in all of science. That's how big of a deal this was. And the reasons why are all right there in the paper. Adam just hit the sweet spot for the modern era of AI. It's fast, it doesn't need a ton of memory, so it's perfect for running on GPUs. It handles problems with millions or even billions of parameters like a champ. And maybe the best part? It just works. The settings are super intuitive, which meant researchers could stop fiddling with their optimizer and actually focus on building cool new models. So because of all that, Adam just became the go-to, the default optimizer. It really is the unsung hero, quietly working in the background, training many of the massive transformer models that power the generative AI systems that we all use every single day. It was the tool that finally gave our blindfolded hiker a reliable way to navigate the ridiculously complex landscapes of modern AI. And that kind of leaves us with this one final thought. The big breakthrough with Adam wasn't some totally new thing pulled out of thin air. It was about taking the best ideas that were already out there, momentum and adaptive learning rates, and combining them in a new, more powerful way. It really makes you wonder, as AI keeps getting more and more complex, what's going to be the next great synthesis that pushes the whole field forward?